Good day, I'm Norman Wildberger. In today's video, we're going to be looking at mathematical space and starting a discussion about what mathematical space is and how we orient ourselves towards having a proper theory of mathematical space, which doesn't involve the infinities that are usually associated with a real number treatment. So we're going to be talking about some basic orientation here, and I want to get at this fundamental duality in geometry, which is not widely appreciated. Very important that you get a sense of the fact that there's really two sides of the coin when it comes to talking about space in mathematics. Okay, so a natural question is, what is space? Well, this is largely a physical and philosophical question. The physicists are very interested in the fine structure of space, but we know that our resolution, our ability to understand things, to see smaller things, is sort of limited, roughly to about 10 to the minus 30 meters. And beyond that, our capability of understanding what's going on is rather limited. So we only have a partial understanding of what physical space really is about. And also, complementary to that, we don't really know what space looks like in the very large. We don't have a very good idea of the large-scale structure of our universe. There are all kinds of philosophical questions that have been discussed and debated about this issue over many centuries. In particular, Kant had very important ideas about the nature of space and our understanding of it. But what we want to do is free ourselves to a certain extent from physical or philosophical discussions. So we want to ask, how do we mathematically represent space? This is a mathematical question. Okay. So there's three key insights that I want to share with you that I think really help us orient ourselves in the right direction with regard to this question. The first is to acknowledge this fundamental duality, that there is an affine and a projective view of space, and that they are complementary. So I'm going to explain these terms, but you should appreciate right from the beginning that there are two ways of thinking about things. An affine way, whatever that is, and a projective way, whatever that is. Neither of them are really more important than the other. You should think of them as complementary. Secondly, that space comes in many dimensions. Of course, the space that we live in appears to be three-dimensional, perhaps four-dimensional if we include time. But Euclid, of course, also was very interested in the two-dimensional situation of geometry in the plane or on a page. But it's useful to think about space as actually occurring in many possible dimensions, and not just starting with two. Also, one-dimensional space is very interesting, as we'll see. This might be an example of a one-dimensional space. A zero-dimensional space, that's also at least worth mentioning, which is maybe just a point. Maybe not too interesting. But the one-dimensional space we'll see is very interesting and contains all kinds of very fascinating relations. And then there's this natural hierarchy, 1 dimensions, 2 dimensions, 3 dimensions, and so on. And we should keep this in mind, that there's a sort of a hierarchy of possible dimensions to think about when we're thinking about space. And finally, that arithmetic is the building block. This is really the Cartesian insight that changed the direction of mathematics so much in the 17th century. Descartes, Fermat's idea that we could really pin geometry down to a prior theory of arithmetic. Of course, the arithmetic for us will be the arithmetic, at least to begin with, of rational numbers. That will be our main model for arithmetic, and so that will be the main tool, or arithmetical tool, that we use to build up our notion of space. Okay, so three very important initial orientations that you might like to think about. The Cartesian revolution in geometry, initiated by René Descartes in the 17th century, changed our view forever about what geometry is. And one way of saying what was happening is that a coordinate system, a fixed coordinate system, is introduced, and in the plane, it allows us to represent points by ordered pairs of numbers. So here's an x-axis, a y-axis, but you note that I haven't made them exactly perpendicular. And also the scale on the axes isn't really corresponding. Here the scale seems smaller than the one in the y direction. Nevertheless, once we have such a framework of axes, we can use notions of parallel lines to represent points by ordered pairs of numbers, namely the x-coordinate, in this case 2, and the y-coordinate, in this case 1. So we can say this is the point 2, 1, and note that we're going to use square brackets to denote points, which I generally like to do. In addition to points, we can also talk about lines and more general curves by thinking about equations in x and y. For example, the equation x squared plus y squared equals 1, the equation of a circle, which in this case looks something like this. It doesn't quite look like a circle here because the axes have been scaled in different ways, so it actually appears as an ellipse. Okay, so very powerful idea. We've talked about this before. The idea that once we have fixed axes, we can talk about points very concretely in terms of ordered pairs. We can talk about curves, lines, in terms of their equations. And we have to also mention that, in fact, the idea of coordinates is not entirely new, not entirely a 17th century idea. The ancient Greeks did use coordinates, for sure. Apollonius, for example, used coordinates in his study of conics. For example, he had a notion of conjugate diameters, that if you take the center of an ellipse like this and you draw any line through it, you can call that a diameter. Okay. And this diameter is bisected by that center, so this segment is equal to that segment. And then he noted that if you take parallel lines and you also bisect them, so you split them in two, you get these midpoints which end up lying on another diameter. And then if you look at lines which are parallel to this diameter and you split them in two as well, bisect them by these points here, then you recover the original diameter. So we call these conjugate diameters, and he realized that they provide a framework for investigating properties of a conic, basically a coordinate system very much in this direction, except that the coordinate system is sort of built from the conic, whereas in this view we start with the coordinate system and then we think about arbitrary curves within that fixed coordinate system. Okay, but in any case, it's a very important idea, and it allows us to reduce questions of geometry to questions of algebra and essentially arithmetic. Of course, it depends very much on us having a prior understanding of the numbers that we're using to label one axis in particular. Okay, so now we can follow Descartes and introduce an affine view of geometry. So we're going to define what points in various dimensions are. And we're going to here work over the rational numbers, which means that all numbers will be rational numbers unless otherwise specified. All right, so here's some definitions. Definition of a 1 point, definition of a 2 point, definition of a 3 point. Okay, so what is a 1 point? A 1 point is an expression of this form. It's an expression involving a square bracket, a number, and another square bracket. A left square bracket, a right square bracket, and inside is our rational number, say little a. And this object will typically denote by a capital letter, like capital A. So this is what we mean by a 1 point. A 2 point, on the other hand, is something rather similar, except that it has two rational numbers inside, separated by a comma. So left bracket, A1, comma, A2, right bracket, where A1 and A2 are rational numbers. That's what a 2 point is. And a 3 point, well, very much the same kind of thing, except that now we have three rational numbers, A1, A2, and A3, separated by commas inside the square brackets. So notice that we're not just defining point, we're defining things a little bit more precisely. First 1 points, then 2 points, then 3 points. And you could see that we could very easily carry on and define 4 points, 5 points, and maybe n points. And in a little while we'll do that. But for now, let's just stick with these 3 different kinds of points. Now note that the definitions that I gave of the 1 point, 2 point, and 3 point are independent of any pictures. I didn't show you any pictures that go with the definitions. The objects themselves were defined purely algebraically, purely in terms of how we actually write them down. That doesn't mean that these concepts have no geometric meaning. Not at all. Rather, it means that we do not specify which geometric meaning they have. We allow the possibility that the expressions that we are writing down can be interpreted in quite different ways by different people. So yes, we may have a geometrical meaning in mind, but somebody else may have a somewhat different, or maybe completely different geometrical meaning to the expressions that we write down. So this is a sort of an expression-oriented view, and for those of you who have watched my earlier video, which is entitled something like Expression versus Object-Oriented Mathematics, you will know that I'm inclined towards the importance of expressions. Okay. So, for example, suppose you have the 2 point 2, 1. Right. So one view, perhaps the most familiar view of what that means, is this one here. We have an x-axis, a y-axis, equal scaling along both axes. The axes are perpendicular. It's our standard Cartesian plane. We have 2 in this direction, 1 in this direction. That's the point 2, 1. So we have this mental image that the 2 point 2, 1 represents that point in this picture. But it might be possible for someone else to come along and say, okay, I'm going to draw my x-axis in this direction and my y-axis in this direction. And I'm going to make the scaling along the x-axis perhaps different from the scaling along the y-axis. I can still use the same idea. I can still draw lines which are parallel to the axes to find the point, which is 2 over in this x direction and 1 over in the y direction. And I can plot it there, and I can say, there's the point 2, 1. Somewhat less familiar, we could also perhaps imagine a situation where in some application it's useful to have a different kind of coordinate system. Maybe one that's not made out of straight lines, but that has some parabolas involved. So here's a coordinate system that has lines, vertical lines as usual, but instead of having horizontal lines, we seem to have parabolas. Right? So if this is the origin, then this would be the x-axis. And here is the line y equals 1. Here is the line y equals 2. Here's the line y equals minus 1. Okay, so for some purposes it might be interesting to think about geometry in this context. In that case, where would the point 2, 1 be? Well, one natural interpretation to say, all right, this is the origin. We should go 2 in the x direction. We should go 1 in the y direction. We should sort of be consistent. And so maybe this point up here is a natural candidate for the 2 point 2, 1. And there might be quite a lot of other different ways of thinking about things. The point is that algebraically we're defining the 2 point rather simply. A computer has no problem in checking that this is a 2 point because the computer looks to see a left bracket, yes, and then a number, and then a comma, not a period or a semicolon or anything else. It has to be a comma, and then another irrational number, and then a right bracket. And the brackets are square brackets. All right. The computer can check those things and say, yes, that is a 2 point. The computer doesn't have to concern itself with what it actually looks like. I'd like to draw your attention to the case of the 1 point. Deceptively simple. So here's a 1 point. Its name is A, and it consists of the number 4/3 in square brackets. Notice that this object is a different kind of object than a number. It's not really the same as the number 4/3 because it's enclosed in square brackets. the computer can tell that this is something different from a number because of the existence of those square brackets around it. Okay, so we're going to have to introduce new types of mathematical objects, which is something we like to do, expanding our horizon, expanding the range of things that we can talk about. Okay, so let's start with 1 point. Here's a 1 point, A. Square bracket, number, square bracket. What should we say? Well, let's say that this is of type, well, it's maybe logical to say rational with square brackets around it. So we'll say rat with square brackets around it. That is the type of this object. We shouldn't say that it's of type rat just by itself because it's not a rational number. It's something different. It's a rational number in brackets. So we're going to use this notation to specify the type of this object. Now, this might be a little bit cumbersome sometimes, so we introduce a variant. We're going to say that A super 1 is another name for this type of object. Basically, affine 1 space. A for affine. A 2 point, like this one here, is of type, okay, we might introduce this idea, rat with a square up there, also everything in square brackets. That means a 2 point. And a shorter way of describing that, maybe A2, standing for affine two-dimensional space. And a 3 point, like this one, well, that's of type rat cubed in square brackets. Or A cubed. So we use these symbols A super 1, A super 2, A super 3 when the number system is already known. In this case, we have before said that we're going to be working over the rational numbers. But it might be later on that we are a little bit more flexible about what number system we want to use. That's going to be very important, in fact. So we allow ourselves the future possibility that these rational number systems in here are going to be replaced with something else. Okay? So we'll still use this kind of generic type when the number system is fixed and known, but maybe it's rationals and maybe it's something else. Maybe it's a finite field or a finite extension field of the rationals. These are things that we're going to talk about in the future. Okay? But they are going to provide extra domains or extra places where we can think about geometry. All right, so this is sort of interesting notation, some new very elementary kinds of objects just built from our rational numbers by putting them in square brackets and perhaps stringing a few of them together. And this is the affine view of geometry. It's one that will be very familiar to you because if you've done high school geometry, university geometry, you're very familiar with points as ordered pairs or triples of numbers and so on. Now I want to turn to a much less studied point of view of geometry, the other side of the coin. Instead of the affine view of geometry, there's a projective view of geometry, which is ultimately mathematically just as important as this affine one, even though these days it sees much less development. Unfortunately. Maybe we can start turning that around a little bit, okay? So projective geometry, very important subject that really needs to be reintroduced into schools and universities. So let's have a look at the fundamentals of projective geometry. So the idea of projective geometry really goes back to the ancient Greeks. And you might have a look at the Math Foundations 20 video, which is about Euclid and proportions. So the idea of proportions is going back to the ancient Greeks, and it's the key sort of idea in setting up projective view of geometry. So here's the main definition, that a two proportion is an expression of the form A to B. This is a colon, 2 dots. We'll read this as A to B, where A and B are numbers. For us, that means rational numbers. Not both 0. They cannot both be 0. One of them can be 0, but then the other one has to be non-zero. They cannot both be 0. With the convention that a to b equals lambda a to lambda b for any non-zero number lambda. We're talking about the proportion between two numbers. You have two numbers, and it's the proportion between them, or sometimes the ratio, if you might like to think. That's also a valid way of thinking about it. The ratio between those two numbers is what we're interested in, and if you scale both of them by the same factor, then the ratio or the proportion doesn't change. So for example, the proportion 3 to 4 is the same as the proportion 6 to 8. This proportion are related by the fact that if I take lambda equal 2, multiply both of these by 2, then I get this one. Here's one proportion, 1/2 to 3. That's the same as 3/2 to 9. How did I get this one from this one? I multiplied both of them by the number 3. How about 1 to 0? That's a legitimate proportion. That's equal to 7 to 0. Why is that? I just multiplied both of these by 7. It's also equal to minus 7 over 4 to 0. I multiplied both of these by minus 7 over 4. And this proportion, 0 to minus 5, well, that's the same as 0 to 17 over 19. I multiplied by minus 17 over 19 times 5. 5 in the denominator. Okay, note again that 0 to 0 is not a valid two proportion. Okay, this is not in the realm of two proportions. Okay, so this idea plays a very important role in my book, which is called Divine Proportions. Okay, my book on rational trigonometry and universal geometry. And in fact, on page 25, this definition is taken directly from there. Okay. Of course, you should all read my book at some point, right? Yes. Okay, so this is the fundamental basic idea of a two proportion. So let's observe that every two proportion can be rewritten as a proportion between integers just by clearing fractions. That's an attractive aspect of working with proportions. In fact, it becomes quite important in computer science, having to do with transformations of three-dimensional space. This is a very important and useful aspect of dealing with proportions rather than dealing with numbers directly. So for example, if we have the proportion 2/3 to 4/5, it might be a little bit unwieldy because we're dealing with these fractions. Well, we can multiply both of them by 15, the least common multiple there, to get 10 to 12. Of course, we could also rewrite that as 5 to 6. So almost all two proportions can be written in the canonical form r to 1. The same kind of idea that as long as the second number is not 0, we can multiply both sides by the inverse of that second element. So for example, if we have 2/3 to 4/5, we could rewrite that by multiplying both of them by 5 over 4. That renders that second one equal to a 1. And we get 10 over 12. So we can rewrite it as 10 over 12 to 1 or 5 over 6 to 1. This is another useful flexibility that we have when we're dealing with proportions. So one thing we can do with proportions is we can clear denominators. Another thing we can do with proportions is we can arrange that the second entry is 1. At least almost all the time. The exception is, of course, 1 to 0. There's nothing that you can multiply this particular proportion by to arrange that that second element is 1. Right? So this one here cannot be scaled to this form. Alright, so if you've been watching this series, you will already have some experience thinking about proportions, because we talked about this kind of thing in the Math Foundations 103 and 104 lectures, when we were talking about extending the rational numbers to include infinity. You may remember that lines through the origin, homogeneous coordinates, played a big role, and that's really the same kind of thing that's happening here. All right, so how do we get geometry out of these proportions? All right, so here's the key definition, that a projective one point is an expression of the form P equals A to B, enclosed in square brackets, where A to B is a two proportion of rational numbers, just the kind of object that we've been talking about. So if we take a two proportion and we enclose it in square brackets, then we get a projective one point. We visualize such a projective one point as the line in two-dimensional space through the origin and the point A, comma, B. So here's two-dimensional space. Suppose we're wanting to visualize the projective one point 2 to 1. Well, what we do is we take the point 2, comma 1, which is exactly this point here, and we think about this line that passes through that point and the origin. This line contains not just this point here, of course, it contains all multiples of that point. So if we multiply this point by 2 to get 4, 2, then that will also lie on the line. If we multiply it by minus a half to get minus 1 minus a half down here, it will also lie on that line. So the notion of equality involved in the two proportion is exactly the notion involved in identifying all of these points which lie on this line, with the exception of 0, 0, which is not officially a two proportion. Okay, and we should give this new kind of object a type. For now, let's introduce this sort of simple-minded idea that we're going to denote the type of a projective one point with the following expression. Square brackets, and inside rat to rat. Okay. So we're just reminding us that there's a colon involved. That colon is representing a proportion or a two proportion. And a short form, sort of analogous to the A1, is a P1, a capital P with a 1. I also want to draw your attention to the idea that we're going to think about projective one points as being labeled by small letters in general. So capital letters for the one points that we talked about earlier, and small letters for these projective one points, just to help keep them a little bit separate. So we started talking about one points like this, and now we've introduced projective one points like this. If we're talking about both of them at the same time, it's sometimes useful to think about this one as an affine one point. So we can use that notation or terminology. All right, so now I want to talk about the relation between affine and projective points, in this case just one points. So there's a natural association between this affine one point, consisting of the rational number a, and the projective one point, which is given by the proportion a to 1. Given any rational number, we can cook up this two proportion. So that allows us to go from an affine one point to a projective one point. And this is a natural association between affine one points and projective one points which are not of the form 1 to 0. Something like this particular projective one point doesn't correspond to any affine one point. And there's a very important geometrical picture which I've drawn quite a few times in my various videos, but it's worth reviewing. So here's two-dimensional Cartesian plane, x-axis, y-axis. Here's a point RS. It's actually a point. X-coordinate R, y-coordinate S. There it is right there. The line through that point and the origin, that line is what we can think of as the projective one point R2S. Okay. And that projective one point can be rewritten as R over S to 1, at least if S is not equal to 0, as it is in this situation here. And geometrically, that's telling us that the point RS is on this line, but also this point here, the point R over S comma 1, is also on that line. just obtained by scaling this point by dividing it by s. So we divide both coordinates by s, we get this point down here. And then that lies on this line with coordinate y equals 1. This is a way for us to associate two points, affine 1 points, which we can think of as being on this line, to projective 1 points, which we can think of as lines like this. So to a projective 1 point like this, we can associate that affine 1 point right there. And correspondingly to an affine 1 point, which we can think of as being on this green line, say that one there, we can associate a projective 1 point like that. The only projective 1 point which doesn't get included in that story is this horizontal one, which I've drawn here. Its coordinates are 1 to 0. And in some sense this plays the role of infinity in a way that we've seen before when we were talking about extending the rational numbers to infinity in those earlier 103 and 104 lectures. So we have this sort of understanding geometrically that the projective one-dimensional space is equal to the affine one-dimensional space together with one more point, which we might call infinity, which is really just this special projective 1 point, 1 to 0. Okay, what about projective 2 points and projective 3 points? Well, we can talk about those later, but because projective geometry is so much less familiar to most students than affine geometry, it's probably good to stick with just the one-dimensional projective situation for now. In my next video, I want to now explore a little bit about some remarkable mathematics that we can see even in the one-dimensional situation that we've been talking about. In fact, even in the affine one-dimensional situation. And this will be a really good example of opening our eyes to the wonders of looking at things algebraically rather than transcendentally. Restricting ourselves to finite operations that we can actually do rather than talk about infinite operations that we can't really do but just can't talk about. Okay, so we're going to see very specific examples of concrete mathematical results that are visible from this logical, clear algebraic point of view. In fact, I'm going to show you what, in my opinion, is the second most important theorem in all of mathematics. Okay, the second most important theorem in all of mathematics we're going to see next time in the affine one-dimensional case. Very interesting and important insights to be obtained here. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.